Let's read the question together. The Haber process is an important industrial reaction to make ammonia. This is called the rubric or the introduction of the question, and often the examiners will give us some key information. So they've told us that it's about the Haber process, and they've told us that the Haber process makes ammonia. So I've underlined those key points just so I can refer back to them. Part A. Balance the symbol equation for the Haber process. So, what is the command word? The command word is balance. What other key information has the examiner given me in the question? We're doing a symbol equation and it's for the Haber process. So let's have a little look. They've given us the symbols, so we know that nitrogen, diatomic nitrogen, reacts with diatomic hydrogen to make ammonia, which has the formula NH3. So let's try and balance it. Here we've got diatomic nitrogen, a molecule of nitrogen. So we've got 2 atoms of nitrogen. Here we've only got 1 atom of nitrogen. So we need to put a large number 2 in front of this to mean 2 lots of ammonia is made. Now let's consider the hydrogen. If we've got 2 lots of ammonia, we've got 2 times 3, that's 6 atoms of hydrogen. But here we've only got diatomic hydrogen, which is 2 atoms of hydrogen. So I need to put a 3 in front of this to mean 3 lots of hydrogen molecules. Now, just because there's a line here doesn't mean you need to fill it. And we're not going to, because here we've got the diatomic nitrogen, 2 nitrogens, and here we've got 2 nitrogens in the 2 separate molecules of ammonia. Now remember, it's super important that a symbol equation is balanced because no atoms are created or destroyed in a chemical reaction. They're just rearranged. So we need the same number and type of atoms at the start, the reactants, as in the products at the end. Part B. The forward reaction is exothermic. Complete the energy diagram in figure 3 for this reaction. This here is figure 3. So what is the command word? The command word this time is complete, and that means the examiner started something for you, you need to add to it. Now what's the key information here? The key information is the forward reaction because of course these are reversible arrows here, which means it's a reversible reaction. So the forward reaction is exothermic. So when the nitrogen and hydrogen react to make ammonia, that is exothermic. And the backwards reaction therefore would be endothermic. And we want to complete the energy diagram in figure 3 for the reaction. So if the reaction is exothermic, it means energy is given to the environment from the system. So therefore, the products will have a lower energy level than the reactants. So I'm going to start by doing that. And I like to label it. Now what actually happens is you have an amount of energy that goes in to start the reaction, and that is the activation energy. So the energy level will actually go up to begin with and reach a peak, and then it will go downwards to finish off with the products. And that now completes the diagram. So what are we getting the marks for? Because this is a 2-mark question. You get 1 mark for putting the activation hill, and you get 1 mark for putting the products less than the reactants in terms of energy. Let's look at part C. In industry, an iron-based catalyst is added to the reactor. Add to figure 3 to show the effect of a catalyst on this reaction. So what's the command word? It's add. Now we're going to add something else even more to the figure that we've got here. What extra information has the examiner given us? That we use an iron-based catalyst, and we need to show the effect of the catalyst on the reaction. Now, a catalyst lowers the activation energy, and in doing so, more collisions will have enough energy to react. So it doesn't mean that there are more collisions, the number of collisions is the same, it's just the number that can react is greater. So remember, this hill bit here is the activation energy, and it needs to be less than because we've added a catalyst. And there we go.